We began our study of modern algebra with group theory, and recently we've been studying field theory, having moved through ring theory on the way. Galois theory is the structure that basically brings it all together. As it turns out, the concepts of field extensions and the net of all subfields of a given field is intimately related with the concepts of the subgroups of a group. So Galois theory connects these two concepts together very explicitly and allows us to conclude many very interesting things, usually by taking groups which are easier to understand and using the various theorems that we're going to employ to prove things about field extensions. So we begin with the Galois group in definition 176. Let's let E be a field, and given this a ring isomorphism, a ring isomorphism phi from E to E is called an automorphism of E. So it's a field isomorphism from a field to itself. Now, of course, the identity function is always an automorphism of a field, but a field can have lots of other ones as well. And while we usually aren't interested in the set of all automorphisms of a given field, what we are usually interested in is the set of automorphisms that fix a given subfield. So given a subfield, f of E, the Galois group of E over F, which is denoted GAL E over F, Galois group of E over F, is the set of all automorphisms of E which fix every element of F. Symbolically, we can write this that the Galois group of E over F is the set of all phis from E to E, where phi is an automorphism, and we have that phi of x is equal to x for all x in F. Now, a brief note about the notation here. Even though the notation Galois group of E over F uses this slash, which is the similar notation to what we used for factor groups, this is not referring to, say, a factor ring of E over F. F is not generally an ideal of E, so that would not even make sense. So we should think of this slash as just being part of the same notation for the Galois group, and without any further meaning, ring theoretically. Now, if we have some subgroup of the Galois group, then H is a set of automorphisms. And we can define this set EH, and it's going to be the set of all elements of E that are fixed for all phi that belong to H. And this is called the fixed field of H. So it's the set of all elements that are not changed by any automorphism in H. So notice in particular that this means that F is a subfield of EH for all H, which is a subgroup of the Galois group of E over F. Because any element of the Galois group of E over F fixes all elements of F, and therefore anything in F is in the fixed field of any element of the Galois group. Now, the group operation on the Galois group is composition. The identity element of the Galois group is the identity automorphism that just takes x to x for all elements x of E. Because all the elements are isomorphisms, they have inverses, and so it's very easy to check the group axioms for the Galois group. So when we say the Galois group of E over F, it is truly a group under composition. So let's see if we can compute a few Galois groups. So we claim that the Galois group of the complex numbers over the real numbers is isomorphic as groups to the group Z mod 2Z. So let's see how this goes. So for any phi in the Galois group of the complex numbers over the real numbers, and any element a plus bi in the complex numbers, we have that phi of a plus bi is equal to, since phi is a ring homomorphism, this has to be phi of a plus phi of b times phi of I. Now, because phi is in the Galois group of C over R, then phi has to fix all of the elements of R, meaning if we put any real number into phi, we need to just get that back. So a and b here are real numbers, so phi of a is a, phi of b is b, and the only thing that might be different here is phi of I. So we can look and see what are the possible values of phi of I, because clearly any element in this Galois group is just determined by where it sends phi of I. So phi is determined by phi of I. However, we also have that I squared is equal to 1, negative 1, rather. So that means that phi of I squared has to equal phi of negative 1. Now, negative 1 is a real number, which means phi fixes it. Phi of negative 1 has to equal negative 1, and we have that phi is a ring homomorphism, so that means that phi of I squared is equal to negative 1. Well, there are only two possibilities here. That means that phi of I has to either equal I or phi of I equals negative I. Those are the only two values of I that would make this statement true. That phi of I squared is equal to negative 1. So there are exactly two elements of the Galois group of complex numbers over the real numbers, namely the identity automorphism on C, which takes a plus bi to a plus bi, and the conjugate automorphism, which takes a plus bi and maps it to a minus bi, which takes I to negative I. Furthermore, let me call this conjugate automorphism phi. And then furthermore, we have that phi squared is equal to the identity. So we can construct an isomorphism from the Galois group of C over R to the group Z mod 2Z, where the identity function on C maps to the 0 element and the conjugate automorphism maps to the element 1 bar. So in this case, we can see that the Galois group is very simple. Now it's going to turn out, as we're going to see in the next lecture when we get to the fundamental theorem of Galois theory, that this means that there are only two subfields of the complex numbers that contain the real numbers. So only two fields that lie between the real numbers and the complex numbers. And it turns out those are exactly the real numbers and the complex numbers. So there is, what this will show when we combine it with the results we're going to get a little later, is that there exists no field strictly between the real numbers and the complex numbers. It's interesting to try to prove that directly. It can be done, but this is an interesting approach to it. All right, let's do another example. Let's let E be an extension field of the rational numbers, the smallest field containing the rational numbers and the square root of 2 and the square root of 3. Now, based on things that we saw in the last section, we have that E is given by A plus B times the square root of 2 plus C times the square root of 3 plus D times the square root of 6, where A, B, C, and D all belong to the rational numbers. And in fact, the elements 1, square root of 2, square root of 3, and square root of 6 form a basis for E as a vector space over Q. So let's try to determine the Galois group of E over Q. So similarly to how we did it before, we have that any phi in the Galois group of E over Q is determined by phi of square root of 2 and phi of square root of 3. Now, this is because phi is fixed on the elements of Q, so for any element of E, phi of A will be A, phi of B will be B, phi of C will be C, phi of D will be D. So if we know where phi of square root of 2, what phi of square root of 2 is and what phi of square root of 3 is, then we can also figure out what phi of square root of 6 is, because phi of square root of 6 will be phi of square root of 2 times phi of square root of 3. So any element of the Galois group is determined entirely by where it sends the square root of 2 and the square root of 3. But just like how we did things before with the complex numbers, we have that phi of the square root of 2 squared would have to equal phi of 2, which is 2. So that means that phi of square root of 2 has to equal plus or minus the square root of 2. And similarly, phi of the square root of 3 squared is phi of 3, which is 3. So phi of the square root of 3 has to equal plus or minus the square root of 3. So that means that the Galois group of E over Q has 4 elements, and each of which is its own inverse. In other words, every element of this group has order at most 2. So we have the identity automorphism on E, which sends the square root of 2 to the square root of 2, and the square root of 3 to the square root of 3. And then we have 3 more. I'm going to call phi1 the function which sends the square root of 2 to negative square root of 2, and the square root of 3 to the square root of 3. Phi 2 is the square root of 2 to the square root of 2, and it sends the square root of 3 to negative square root of 3. And then we have phi 3, which sends the square root of 2 to negative square root of 2, and the square root of 3 to negative square root of 3. So we have these 4 different elements which make up the Galois group of E over Q. Now, recall that there are only, up to isomorphism, there are only 2 groups of order 4 up to isomorphism. We've got Z mod 4Z, the cyclic group of order 4, and we have Z mod 2Z direct sum with Z mod 2Z. So the Galois group of E over Q must be isomorphic to one of these 2. And to identify which it is, we can go back to looking at the orders. As mentioned, these automorphisms all have order at most 2. So the order of the identity element is, of course, the identity, and the order of all the other elements in here are 2 because they are their own inverses. So that means that the Galois group of E over Q can't be isomorphic to Z mod 4Z, which contains an element of order 4. It must be isomorphic to Z mod 2Z direct sum Z mod 2Z. So we can write this down. We have that the Galois group of E over Q is isomorphic to Z mod 2Z direct sum Z mod 2Z. And we can recognize this in the following way. We can basically send an element of the Galois group to a pair over here where the first entry is 0 if the square root of 2 is fixed and 1 if otherwise, and the second element is equal to 0 if the square root of 3 is fixed and 1 otherwise. So this means that phi 1 from the previous page sends the square root of 2 to negative square root of 2, so we'll attach it to the element 1 comma 0. Phi 2 is one that fixes the square root of 2 but sends the square root of 3 to its opposite, and then phi 3 sends both the square root of 2 and the square root of 3 to their opposites. So from this we can see that the group structure is maintained. So over here on the right, we have that 1, 1 is equal to 0, 1 plus 1, 0. And that's identified on the left by noting that phi 3 is the composition of phi 1 and phi 2. Also notice that in this case, the Galois group happens to be abelian, which is, of course, not generally the case because the operation is composition, which is generally not commutative. We can also identify some correspondences between the subgroups of Z mod 2Z, direct product Z mod 2Z, with the Galois group. So looking at subgroups here of Z mod 2Z direct sum Z mod 2Z, it turns out there are only 5 subgroups of this group. We have the trivial subgroup containing only the element 0, 0. We have the subgroup containing 0, 0 and 1, 0. The group containing 0, 0 and 0, 1. The group containing 0, 0 and 1, 1. And the whole group itself. Now, these can correspond to subgroups of the Galois group. And so the element 0, 0 corresponds to the Galois group, which is just the trivial subgroup containing the identity. Then we can have that the subgroup 0, 0, 1, 0 is the subgroup generated by 1, 0, which corresponds to the subgroup generated by phi1. And then we've got the subgroup generated by phi2. And then we've got the subgroup generated by phi3. And then finally, the whole group corresponds to the whole group. So let's look at the fixed fields of these various subgroups. We have that the fixed field of the identity element, this is going to be the set of all elements of the field E which are fixed by the identity automorphism. But every element is fixed by the identity automorphism, and so we have this. We have that the fixed field of the identity subgroup, or the subgroup containing just the identity, is the whole field. Now we have that the fixed field of the subgroup generated by phi1, this is going to be all of the elements of the field which are fixed under phi1. So it's going to contain all the elements that look like a plus b square root of 3, where a and b are rational numbers. Because anything with a square root of 2 in it will not be fixed, because phi1 will send square root of 2 to negative square root of 2. Now this we can recognize as the field q of square root of 3, the smallest field containing q and the square root of 3, which certainly lies between the rational numbers and e, which is the smallest field containing both the square root of 2 and the square root of 3. Now, the fixed field of the subgroup generated by phi2 is going to, by a similar argument, be a plus b square root of 2, which is q of square root of 2. Now, the fixed field of the subgroup generated by phi3, remember that phi3 sends square root of 2 to negative square root of 2 and square root of 3 to negative square root of 3. What it's going to fix is the square root of 6, which is the product of those two. So that's going to give us the field q square root of 6. And then finally, the fixed field of the whole Galois group E over Q is going to be just Q. So Q is the only field that's fixed by every automorphism inside the Galois group. Now we can actually look at the net of subfields of E over Q and the net of subgroups of the Galois group of E over Q, and we're going to see a strong relationship there that we're going to exploit via the theorems of Galois theory. So in this particular example, for instance, we can look at the subgroups of the Galois group E over Q. So at the top, we've got the whole group, the Galois group of E over Q. And then below that, all the way down at the bottom, we have the subgroup containing just the identity element. And then in between, we had three subgroups, phi1, phi2, phi3, which all lay between those two and don't have any relationships between themselves. Now, if we look at the subfields of E over Q, we have E at the top, we've got Q at the bottom, and then we've got q square root of 3, q square root of 2, q square root of 6, all going up to e like this. And what you'll notice is that if we compare the subgroups over here with the fixed fields of those subgroups over on the right, we could have obtained the subfield diagram over here on the right by taking the subgroup diagram, flipping it vertically, and then taking the fixed fields of each of these subgroups. So Q is the fixed field of the Galois group of E over Q. E is the fixed field of the identity subgroup. Q square root of 3 is the fixed field of phi1, Q square root of 2 is the fixed field of phi2, and Q square root of 6 is the fixed field of phi3. This relationship here is not an accident, and it occurs very often. Understanding when it does is of central importance to Galois theory, and is going to be the next thing that we look at after we establish two more important theorems that describe the existence of certain automorphisms and the properties that elements of the Galois group need to have. So let's look at theorem 177, which tell us that we can always guarantee the existence of certain automorphisms, or automorphisms that have certain properties. So let's let F be a field. Let's let E be a superfield of F, a field extension of F, which is a splitting field of F. That is the splitting field of some polynomial in the polynomial ring F adjoint X. Now, if A and B are two roots of a single irreducible polynomial, we'll say G, in the polynomial ring F over X, then there exists some element phi in the Galois group of E over F such that phi of A equals B. So if you have two roots of an irreducible polynomial, there is some element of the Galois group that sends one of them to the other. So let's see the proof of this. By theorem 161, we have that F of A is isomorphic to F of B as F extension fields. Furthermore, if we look at the theorem carefully, there exists an isomorphism of F extension fields phi from F of A to F of B, such that phi of A is equal to B. So now let's look at a diagram here. We've got that phi is contained in F of A, but is also contained in F of B. I should have specified up here. These A and B here, they have to be things that actually belong in our set E. So that F of A is contained in E and F of B is contained in E. But now we also have this isomorphism phi, or psi, that sends F of A to F of B. So now we can recognize that E is a splitting field for F of A in two different ways. First of all, we have that f of a is simply a subset of E. But we can also recognize that it's a splitting field where we take f of a, go alongside to f of b, and now f of b is a subset of E. So we can go across and then up. Now, by the uniqueness of splitting fields, there exists a phi from E to E, an isomorphism, and isomorphism of f of a extension fields such that for all x in f of a, we have that phi of x is equal to psi of x. In particular, this means that phi of a is equal to psi of a, which is equal to b. Furthermore, we have that for any element of f, we have that phi of x is equal to psi of x, which is just x, because remember that psi is an isomorphism of f extension fields, and so it fixes every element of f. So this means that this phi is an element of the Galois group of E over F. It's an isomorphism of E. It fixes the elements of F, and it sends A to B. So here we're using the uniqueness of splitting fields in an important way. So Theorem 177 can guarantee us the existence of certain elements of the Galois group. The next theorem tells us a restriction that every element of the Galois group needs to have, which is also very useful, especially when we want to limit the number of elements of the Galois group or understand how many elements there could be. So Theorem 178 says that if F contained in E is any field extension, don't need a splitting field like we did in the last one, phi is an element of the Galois group of E over F, and A in E is the root of some polynomial f in polynomial ring f adjoint x. I really should say a root. Then phi of A is also a root of f. So any element of the Galois group must take roots of polynomials to roots of the same polynomial. Let's see why. Let's let f be given by b0 plus b1x plus b2x squared up through bnx to the n be a polynomial ring over the field f. And let's let A, an element of E, be a root of F. What this means is that in the field E, we have that B0 plus B1A plus B2A squared plus etc. plus Bn A to the n equals 0. So that means that 0 equals phi of 0, because any ring homomorphism must send 0 to 0. but that's phi of b0 plus b1a plus b2a squared, etc., plus bn a to the n. Phi is a ring homomorphism, so this is phi of b0 plus phi of b1 phi of a plus phi of b2 times phi of a squared, etc., plus phi of bn times phi of a to the n. But phi is an element of the Galois group of E over F, which means that phi fixes every element of F. In particular, it fixes all the coefficients of the polynomial little f. So this means that this is b0 plus b1 phi of a plus b2 phi of b, phi of a squared, rather, plus bn phi of a to the n, which is, of course, just f of phi of a. So that means that phi of a is a root of f. This right here significantly restricts the number of elements of the Galois group typically. Typically, we're going to be working with Galois groups which are the splitting fields of some polynomial over the field f, which means that they are the smallest field containing f and some finite number of algebraic elements over the field f, and in particular, what Theorem 178 says is that every element of the Galois group can only permute those roots together. It has to send every root to another one, and because it's bijective, it can't send any of them to the same. We're going to get a whole lot more into this in the next lecture when we start measuring the size of the Galois groups and comparing it to the number of field extensions that exist in significantly more detail.